Okay, so in this video, we want to find the derivative of any exponential function and any logarithmic function. And this is what we have so far. We have the very special exponential function base e. So if you remember, e was roughly 2.71828. It was an irrational number, but it has a really unique property of the derivative of e to the x being e to the x. Ln of x is the log base e function, which is the inverse function of e to the x, and the derivative of ln of x is 1 over x. We will now take any base that is positive for our exponential function, and with the help of this property of logarithms, right, this is true of any logarithm, but here we only care about the special case where the base is e, but we call this ln of x. So if you take the ln of a to the b, as long as a is positive, you can remove the exponent from a outside of the ln. Suppose that we want to differentiate now the exponential function y equals a to the x, where a is any positive number. The key is, once again, we will get rid of the exponential function, and then we will find the derivative using implicit differentiation. So we want the derivative of a to the x. We call that y. So all we want to find now is dy over dx. Well, how can we get rid of the exponential here? Well, the idea is both sides are equal, so take the ln on both sides. So ln of y equals, well, now y is equal to a to the x. So you can replace y by a to the x. You'll have the ln of a to the x. And now since a is positive, we can use the property of the logarithmic function, where ln of a to the b is equal to b ln of a. We can remove the exponent outside of the ln. So this will simply be x times ln of a. And now, well, y is a function of x. Y is a to the x. And so ln of y is also a function of x, is equal to x ln of a, which is also a function of x. Keep in mind that now a is the base of our exponential function, so a is a constant. So ln of a is also a constant. Okay, so as before, we are in the case of implicit differentiation, where we have a y that we know is a function of x. So let's differentiate both sides of the equality with respect to x. So the derivative with respect to x of the left-hand side, ln of y, will be equal to the derivative of the right-hand side with respect to x. Okay, well, let's differentiate ln of y first. We have here a composition, right? If I give you a value of x, you would first plug it in here, take a to the x, so you would first evaluate y, and then you would take ln of y. So the outside function here is ln, and so we differentiate ln, and the derivative of ln of something is 1 over that something. So here we'll have the derivative of ln is 1 over what's inside, which is y. By the chain rule, right, this is only the derivative of ln. By the chain rule, we have to multiply what we have so far by the derivative of what's left over. What's left over is y, and so we'll have the derivative of y with respect to x. So this takes care of the derivative of the left-hand side, equals. Now here we have x times ln of a, but ln of a is a constant. Multiple of x, which just stays there, so ln of a, times the derivative of x, which is 1, so it's just ln of a. We can now solve for dy over dx. Multiply both sides by y, so dy over dx is going to be y times ln of a. And if you remember, y was simply a to the x. So this is equal to a to the x ln of the base. And now we have the rule of the differentiation for y, which is a to the x. And we can now state our conclusion. The derivative of y, which was a to the x for any positive base a, so d over dx of a to the x, that is exactly equal to a to the x, so the function itself, times the ln of the base, the ln of a. And so there you have it. The derivative with respect to x of any exponential function base a is the function itself times ln of a, ln of the base. And if you go back and you ask, does this agree with the derivative of e to the x? Well, the derivative of e to the x was e to the x. So if you plug in here, instead of ae, you'd have e to the x ln of e, but the ln of e is 1, so all you would get is e to the x as before. So we now have the derivative of any exponential function. With this, we can now find the derivative of any logarithmic function. Once again, with the help of not logarithmic, but implicit differentiation. So what if we ask now, what if our function is the logarithmic function base a of x? Well, once again, we want to find dy over dx. So we want to get rid of the log base a function, so exponentiate both sides with a. So take a to the y equals, well, because y is the log base a of x, you can replace y in the exponent by log base a of x. And this will be a to the log base a of x. But the logarithmic function base a is the inverse of the exponential function base a, so these two will cancel, and you're left with simply x. And once again, we have this equals x, and we know y is a function of x, so both the left-hand side and the right-hand side are functions of x. We can once again use implicit differentiation. Differentiate the left-hand side with respect to x. This will be the same as the derivative of the right-hand side with respect to x. Let's differentiate carefully here. If I give you an x value, you'll plug it in here, take the log of it, so you will first compute y, and then you will take or exponentiate a to the yth power. So the last thing you do is the exponential, and by the chain rule, you have to differentiate the exponential function. Well, the derivative of the exponential is the same thing, so a to the y, but times the ln of the base. The base is 8, so times ln of 8. But that's just the derivative of the outside function, the exponential. By the chain rule, we have to multiply what we have so far by the derivative of what's left over, which is y, and that is, of course, dy over dx. There's nothing left over, so that's the derivative of the left-hand side, equals, now this is quite simple, the derivative of the right-hand side, the derivative of x with respect to x is just 1. And now we can simplify a little bit, right? A to the y, that's just equal to x. So what we have is x ln of a times dy over dx is 1. Well, if you want to solve for dy over dx, the derivative of the logarithmic function base a, divide both sides by x ln of a. So what you will find is dy over dx is 1 over x ln of a. And if you remember, y was just the logarithmic function base a. So you see we'll have a very similar result. The derivative of a to the x is a to the x ln of a. And now if we ask for the derivative of log base a of x, so d over dx, of the logarithmic function base a of x, what we have is 1 over x ln of a. And this is true for any logarithmic function base a as long as the base is positive. And we can go back to e and see if that agrees with what we have for e to the x and ln of x. You see the derivative of ln of x is 1 over x, but that's, if you remember, ln of x is a special name for the logarithmic function base e of x. So if we replace a by e in our general result, we will get back the previous result that the derivative of ln of x is 1 over x. Well, if you replace a by e, this is ln of x, and the derivative would be 1 over x ln of e, but ln of e is equal to 1, so this would just be 1, and once again we would have 1 over x. So this agrees with a special case of the logarithmic function base e. So you see it's really, really nice. The derivative of the exponential function base e is itself. The derivative of the logarithmic function base e ln of x is 1 over x. And when you change the base, it's almost the same thing. The derivative of the exponential function is itself times ln of the base. The derivative of the logarithmic function is 1 over x times ln of the base. And there you have it. We cannot differentiate any exponential function and any logarithmic function. Always keeping in mind that we have the two special cases for the exponential function base e and the logarithmic function base e. In our next video, we will consider examples of exponential and logarithmic functions with involving power rules, product rules, chain rules, and quotient rules.